Welcome to qnawire.
In this problem, we have another combined gas steam cycle. So we have air coming into a compressor, going out to a combustion chamber, going through the gas turbine, and then going into a heat exchanger before it's exhausted out to the atmosphere. So then on the steam side of things, we have the feed water going through a pump, coming through the heat exchanger into the turbine. Some of that steam is bled off the turbine and reheated, then back into the turbine, and then into the condenser, and then back into the pump. So that's the flow. So now we can, our TS diagram looks like this. We have some efficiencies for the compressor and for the gas turbine, and for the pump and the steam turbine. That should be a little S there. So they're all 80%. So we have 80% efficiency in all our mechanical devices here. We have, let's see here, the high temperature here coming out of the combustion chamber is 950 degrees C. At 7 here, coming in, we're at 300 15 degrees C. And leaving the heat exchanger, the air is at 200 degrees C. And let's see here. That's pretty much it, I think. So I'll be coming back here to this page to refer to these diagrams if I need to from the analysis. So on the analysis side of things, again, temperature at 7, we can get enthalpy at 7. Temperature at 7 and pressure at 7, we can get the entropy at 7. I forgot to write that. So we can get the entropy at 7. Then we get the isentropic entropy at 8 and the pressure at 8. So we can get the isentropic enthalpy at 8. Using the efficiency, then we can get the actual enthalpy at 8. Have the temperature at 9, we can get the enthalpy at 9. And with the pressure, we can also get the entropy at 9. Now at 10, we have the pressure, and then for the isentropic case, the enthalpy at 10 is the enthalpy at 9. So we can get, for the isentropic case, we can get the enthalpy at 10. And then we can get the actual specific enthalpy at 10 using the efficiency. And then coming out of the heat exchanger, we can get the, why am I forgetting to write my variables in here? This would be the enthalpy at 11. We can get the enthalpy at 11 coming out, the gas coming out of the heat exchanger. So now we have, let's see here, turning to the steam side of things, the pump analysis, just as we have done many times in the past. Pressure and temperature coming into the turbine, so we get enthalpy and entropy. In the isentropic case, at 6, we have a quality factor and an enthalpy. And then using the efficiency, we can get the actual enthalpy. And from the actual pressure and the actual enthalpy, we can get the actual quality factor. And then we can figure out what percentage by mass of moisture we have, and it's 1.58% moisture by mass exiting the turbine. Now, we can look at the energy balance on the heat exchanger. And we were given the mass flows in both sides. So an energy balance on the heat exchanger will tell us what H4 is. So we know everything else in here, but we don't know H4. So we can get that. And then we know, let's see, we have the pressure at 3 and at 4. So this is the bleed where they're coming off for reheating. And so at 4, we know So this is kind of a little, we got to be a little tricky here, because with the information we're given, we have to do a little bit of work here to get what we need, because we don't have the temperature at 3. We don't have the temperature at 4, but we know in the isentropic case that the enthalpy at 4 is the same as the enthalpy at 3. And we also know that the efficiency is the equation for the efficiency in the turbine, the thermal efficiency, and we know this value. So what we don't know is we don't know what H4 is, H4S or H4. But what we can do is we can guess a temperature here to get an enthalpy at 3, get an entropy at 3. So then with that entropy at 3 at 4, the entropy in the isentropic case, with that entropy at 4 and entropy and pressure at 4, we can get the isentropic enthalpy at 4, and then we can, let's see here. Now we have an equation. We can get the let's see here. We can basically plug everything in here, and well, we don't know enthalpy at 4. So basically we need to, how did I do this? Enthalpy at 4, we can solve that here, and then what do we need to check? We need to actually check that what else information do we have at 4? So let's see here. How did I do that? I can't remember. Now let's see. Guess the temperature. Get these enthalpies. Get this. So we can get this. So we have these things. We know this, so we can get H4. And now, what is the condition that we need to satisfy? We need to satisfy that, let's see here. So we'll get H4, and then we need to go back and satisfy the fact that we have the pressure. So at 4, we don't know the actual entropy. So we know this, and so we can get the full state at 4 from this equation. So then we can, let's see here. What is the final thing that is going to allow us to determine whether our guess was correct or not? Let's see here. Can't remember how I did this now. Well, basically, I use the software. I use software to do it, but I'm trying to basically see how I did it in a guessing approach. So we get the enthalpy at 4, and so then we have to check what is the inconsistency that needs to be checked to see if our temperature was right. Oh, then we have to get, now we also have the entropy at, so we have the enthalpy at 3 and entropy at 3. All right, that's okay. And this and this. And let's see, what was the condition that I used? So we know this, we know this, we know this, we know this. So we can find what this is. But then we need to make sure that things are consistent. Oh, I know what. Yeah, I'm doing this wrong. So what we need to do is oh, wait a minute. Uh, where is the inconsistency here? We plug the pressure in. We can guess the temperature. We get these things. We can then find this, the guess for this, and then for this we can find this guess. So our guess for H4 would be this, and then we also need H4, so we can get H4, so that would be our guess there, and so that needs to be consistent with the pressure at 4. Yeah, yeah. So that needs to be consistent with the pressure at 4, so that we have a consistency condition so that we can trial and error. Anyway, we get our temperature of 470 degrees Celsius. Basically, it's just an iterative process where you have to do trial and error to guess and make sure basically everything is consistent. Or you can use the software and just have it tell you, which is what I would recommend doing, and which is what I did. But I was just trying to go through the trial and error process with you, and I can't remember. Yeah, this needs to be consistent with this, but we also have you know anything else at 4? Oh, yeah. Well, no. I know why. We already know H4. That's what I'm missing. We already know H4. So what happens is we guess a temperature. We find the enthalpy or entropy and the enthalpy. Then we know when we can get what this is. So we have all of these things. And our consistency check is that we know what this is also. So we need to make sure this is equal. So we do trial and error on our temperature until we make sure this equation is satisfied. That's what it is. I forgot that we already knew H4. So, or we can basically just solve for H4 here and then make sure that, do trial and error until we get an H4 that is this H4. So then once we know all this stuff, we know all the enthalpies everywhere. We can just start plugging in. We know the mass flow rates everywhere. So the power coming out of the gas turbine winds up being about 17.3 megawatts. The power going into the compressor is about 10.8 megawatts. So the net work out of the gas side of the cycle or the plant is about 6,560 kilowatts. Out of the steam cycle, the steam turbine, we get about 5,065 kilowatts. The pump is using 34.8 kilowatts. So we have a net work out from the pump of the net power out is 5,030 kilowatts. So the total, and again, these are all in kilowatts. We're not doing specific things, so we don't have to adjust. So we can just simply add this and this. And so we get a total power out of 11.6 megawatts. We can also figure out what the heat transfer into the combustion chamber is. That comes out to be about 30 megawatts. And so our efficiency then becomes 38.8%.